All right, so in this video, we're going to talk about limits involving infinity. And so a lot of actually what you learned back in college algebra is going to come into play here, in particular with those rational functions. And so when we get started with something like this, we just probably need to take a step back and actually intuitively understand what is about to happen. Now, what I've got here is the limit as x approaches plus or minus infinity. So we're now not approaching necessarily a number like 0 or 3 or whatever. We're approaching plus or minus infinity. And we've got our function 1 over x to the n. And this limit always goes off to 0. Now, there's a couple ways that I can explain this to you. The way that I would prefer you to think of it is you have a 1 up here, and you've got something really, really, really big down here, right? So if you've got an infinity, let's say, take a huge number like 10 million. 1 over 10 million versus 1 over 10 billion versus 1 over 10 trillion, as I keep making this number bigger, the overall fraction is getting smaller. So this thing at infinity trends off to 0. So the way that I describe it and the way you hear me say it a lot is you have this small over big ratio. Small over big ratios at infinity always go off to 0. Now, another way that I can explain it to you, maybe graphically, is if you think of the graph, let's say y equals 1 over x. Well, what does that graph look like? It has an asymptote here at 0. It has an asymptote here at y equals 0. And you're going to be here, and you're going to be here. And so, as you approach positive infinity out here, if you approach negative infinity out here, you're still going off to 0. If I put a squared onto that, y equals 1 over x squared, then you've pretty much got a similar graph, but now you're always positive, and as you approach positive infinity, as you approach negative infinity, once again, you're still at 0. We could go on all day with that, but graphically it makes sense, but the more intuitive way that I hope you're kind of forming your mind to think is that small over big type of thing. So let me get this off the screen here. That's just kind of some scratch work. All right, so let's take a look at an example here. And again, hopefully you'll start to remember some of the things you learned back in college algebra. So we're going to take this limit as x goes to positive infinity of 3 minus 2x squared minus 4x cubed all over 3x cubed plus x plus 1. Now, mechanically, the way that we're going to handle these types of problems is we're going to divide every single term by the highest degree x in the denominator. So we're going to divide every single term by the highest degree x in the denominator, which would in this case be x to the third. So I'm going to divide every single term, top and bottom, by x cubed. So I'm going to carry this limit notation down on every single step. I'm dividing everything here by x cubed. And this should simplify down pretty nicely. So we'd have our 3 over x cubed minus 2 over x minus 4 over 3 plus 1 over x squared plus 1 over x cubed. Now remember, our limit laws say that that limit can go into the numerator separately, into the denominator separately, and it can go to each individual term separately in both of those, which means at infinity, due to this fact right here, that this guy would go off to 0, this would go off to 0, this would go to 0, and this would go to 0. So when all is said and done and the dust settles, all we have left is a negative 4/3 for our final answer. Now, that is the final answer. The problem is over with, but let's go back and think about our college algebra days. In college algebra, I tell my students that when you're given a function like this and you're trying to find the horizontal or oblique asymptote, you need to look at the degree on top versus the degree on bottom. If the degree on top matches the degree on bottom, you have a horizontal asymptote at y equals the ratio of leading coefficients. And that's exactly what just happened for us. The ratio of our leading coefficients would be a negative 4/3. So y equals negative 4/3 is a horizontal asymptote for the original function. So now that we're able to study limits, unlike in college algebra, hopefully it's not so much just trust your math teacher, he's going to tell you the right thing. I can now show you why things are the way they are. Okay, so for the first example there on the left, once again I'm going to do the same thing. I'm going to divide every term, top and bottom, by the highest degree term in the denominator, which would be our x cubed. So I'm going to divide everything by the highest degree x in the denominator. So carrying the limit notation down all the way till we evaluate, that's going to be, and I'm going to skip a couple steps here. I think everybody in their head can divide by x squared. If I divide this guy by x squared, it's going to give me a 7 over x. So 7 over x minus 1 over x squared. Similar on the denominator, I'd have a 5 minus a 1 over x plus 3 over x squared. Okay? Now, when I do this, of course, these go off to 0. And when all is said and done here, we get this 0 over 5, which equals 0. So in college algebra, when the degree on bottom was greater than the degree on top, we said that we had a horizontal asymptote at y equals 0. And that's exactly what you've just found here. You've got a horizontal asymptote of that graph at y equals 0. Okay, now for the last example, you can see the degree on top is bigger than the degree on bottom, and this was generally the case where you came up with a slant or an oblique asymptote back in college algebra. But you can see that it doesn't always have to be that. And so I'm not going to do anything different. I'm going to divide everything by that x. When I divide everything by that x in the denominator, I'm going to get this. An x squared minus 1 plus 3 over x. Okay, divided everything by that x. And in doing so, naturally, this goes off to 0. But I still have this part right here. Now, let me carry it down just one more step so I can be clear with what I'm going to show you. Don't get in the habit of actually taking the infinity and plugging it in here. Okay, you can't plug in an infinity. It's not an actual number, but you can certainly think of it as a big number. So if we take a big number and we square it, we get an even bigger number. And if we then subtract 1, well, we're still at infinity. So this limit here actually goes to infinity. It goes off to positive infinity. And so that's the answer to this particular limit. But what's interesting about it is that the asymptote itself is this guy right here. So you have a non-linear, NLA, non-linear asymptote at y equals x squared minus 1. This one just so happens to be a parabolic asymptote. And so what I would strongly encourage you to do is pause the video, get on Desmos, and graph this function right here along with this function right here, which will serve as its asymptote. And it's really amazing how it all fits in there nicely, just as a linear asymptote would have in your previous graphs. But at the end of the day, you're not doing anything different. I divided everything by this x, ended up with this. And then I did have to go a little further and evaluate, knowing that a big number squared minus 1 was still going to give us a positive infinity as our answer, and then this would have been the resulting a non-linear asymptote of the original graph.